presenting the Bluebird snake trap. Mounted on top of the Bluebird nesting box is a solar module that is responsible for the power generation of this device. Under optimal lighting conditions, the solar module delivers approximately 5.1 volts to the solar power manager. The Solar Power Manager uses maximum power point tracking in order to maximize the efficiency of the solar module. The Power Manager also serves to charge the battery. For this device, one rechargeable 3.7 volt lithium-ion battery is used. The stored energy is then translated to power the BeagleBone Black microcontroller. The BeagleBone serves to control the device and is a part of what allows autonomy of the device. From the BeagleBone are attached several components. The first is an IR sensor, which is responsible for monitoring for snakes. Once the sensor is triggered, a signal relays back to the microcontroller. Power is then drawn from the power bank and is delivered to a counter circuit which will count the number of times the sensor has been triggered. From the counter circuit, the voltage continues to flow through a DC to DC boost converter. This converter takes the input voltage, which ranges from around 3 to 5 volts depending on lighting, and rapidly steps it up to around 20 volts. This voltage is then transferred to the discharge circuit to shock the snake. On the side of the nesting box, the weatherproof housing for the system is located. This housing contains all of the aforementioned components, with the exception of the IR sensor. On the bottom of the nesting box and attached to the pole lies the infrared sensor. Once the sensor detects movement, the system is tripped and the discharge circuit becomes hot very quickly. The discharge circuit starts at approximately 1.5 feet off the ground. The circuit consists of 2 wires wrapped around the non-conductive pole. In between these wires is a small gap. This allows for a potential difference, and as soon as the snake wraps around the pole to climb, it will complete the circuit and be shocked. The wiring for the discharge circuit is run through the pole, with the positive portion on the top section of wire and the ground portion on the bottom section of wire. Now that we've seen an overview of the system, let's take a look at the device in action. The voltage is initially dissipating and will reset to 0 after a few seconds. The counter timer is also reading 0. As soon as the sensor catches the hand waving motion, the counter timer ups to 1 and the discharge circuit outputs 20 volts. The 20 volt output is sustained for a few seconds and will then discharge, awaiting for the sensor to be tripped again. Taking a closer look, we can see that as the IR sensor is tripped, the counter increases and the voltage rapidly jumps from a few millivolts all the way to 20 volts. This process will repeat as long as the snake attempts to climb the pole. For the purposes of this video, the system was powered via a USB connection from a computer rather than a solar circuit. Due to the continuous monitoring of the system, a large amount of memory is required, which drastically slows down the functionality of the device. This illustration shows proof of concept until a more sustainable solution can be applied. We hope that you have enjoyed this presentation on the Bluebird snake trap.
This is the transmit portion of the system. The signal generator is set up at 986 megahertz, transmitting positive 30 dBm. The transmit antenna itself is 9 feet away from the receive antenna. The receive antenna is hooked up to a power meter, measuring the output, and it's about negative 0.5 dBm. The next step is to disconnect the power meter from the receive antenna and connect it to the charge pump.
Here the receive antenna receives the RF signal, which goes to a two-stage charge pump, where that signal is rectified into DC power. The DC power of the charge pump goes into the TI boost converter, which boosts that signal. The boost converter's output goes to both the MyDAC, which is used to monitor the results on the laptop, as well as the microcontroller development board. Once the boost converter leaves cold start, the microcontroller will turn on as indicated by the blinking LED.
Good afternoon. This is Daniel Prada with Group C's project, a smart mailbox. Here is the flexible solar panel that comes across the mailbox, which is connected to the solar controller. Two 9-volt batteries wired in parallel. The DC buck boost module, which is connected to the Arduino R3. The 2-channel relay, DC to DC 5-volt boost module, and the ESP8266 Wi-Fi module. So going over some of the functionalities and some of the electronics that are inside the mailbox. Here is a 5 milliwatt laser. Here is the laser receiver. Once the receiver detects that there is no laser, or the laser has been broken and the door is closed, the UV lights at the sides and at the top of the mailbox will turn on to sanitize the mail. To ensure that the mailbox is closed, we have the ultrasound sensor. Once the UV lights are turned on and the mailbox door is opened, the ultrasound sensor will detect that and the Arduino will turn off the UVC lights. Powering on the product here. We can see the Arduino is receiving 5 volts, drawing around 56 milliamps. See the Arduino powered on. So once the mail person comes, opens the door, puts mail in, blocks the laser, close the door. The ultrasound will start taking the average between the sensor and the door, which is around 23 centimeters, to ensure that the door is closed. And we'll see here shortly the Arduino at full load. Here's 123 milliamps. UV light is turned on. We should be receiving a phone call soon. And once the door has been opened, it should turn off the UV lights. Here we have our phone call, and this is our message.
Hello. You have mail. Message brought to you by IFT.
And here is the Arduino back at idle. As we saw there, the UV lights turned off because the timer has finished. And the mail should be fully clean and sanitized. Thank you.
All right, so this is Group E's submission for our senior project. This is our fully autonomous water vehicle. Right here you see the two motors with the propellers and the speed controllers connected to them going into the airtight container right here. This is the GPS and the GPS mount. And then inside we have the 11.1 volt battery, the Pickhawks controller, the telemetry unit, and the RC receiver.
So for this part of the demonstration, we've moved inside so you can see the computer screen a bit better. And on the telemetry radio, there's a solid green light, which means it's connected. So up here in the corner, you set the baud rate and the COM port to the COM port that you have the telemetry radio hooked into. You hit connect, and it'll take a minute to connect. So once you connect, you can see all the data coming back to the screen. If I tip the boat up a little bit, you'll see the gyroscope move. There you go. And to arm the boat, the first thing to do is to activate this safety switch here. Alright, once that's done, you go to the Mission Planner's Actions tab and hit arm. Alright, so it's armed. And there's 3 flight modes between 2 different toggle switches. So the default one is acro mode, which is a manual mode that uses the controllers. So if I can turn the motors. The next one, if you flip this down, is manual mode, which is pretty similar. It just doesn't use the PID controllers. And then if you flip this up 1 tick, it's autopilot mode, which will run the latest waypoint mission that you've loaded onto it. It's not tracking straight at all. But it turns pretty.
Yeah, it's gonna have a lot of problems with that. It is not wanting to go straight.
Well, I bet the throttle is like significantly different.
Which way does it go? Ooh, it wants to go right, so that or left, so that right one's up real high.
I think it's like not a comfortable.
There you go, yeah.
Kind of hard to.
Yes, the right left are like all the way on. They go all the way over, come back around and back.
Right now you can see it's trying to hold position, and the motors turn every now and then to fight against the wind that's going. So the flight mode we have it in is, it still allows for manual control, but it'll correct against disturbance and maybe the motors being slightly offset. So if I let it go straight, and then I let off the throttle, well, in a manual control mode, it probably would have been pushed by the currents and the wind a little bit, and I think the motors are still a little bit uneven, but it tracked pretty straight there. So another thing it does in this flight mode is it'll correct for overshoot in the turn. So if I really give it a lot of throttle to turn that way, it'll kick in the other motor to make sure it doesn't overshoot at all. Probably just because it's
Oh, so you can direct it, like how you want it to go. It's more than just like the path. It's like it gets on specific GPS, like it started here, but it went over this way to go. Oh. What we could do, it might have a lot of leftover momentum. Oh, right. And what we could do, we could say go to the spot and just wait a couple of seconds and then turn. You can add in delay command. So, there, you got the problem finding the line. Kind of cool how I know it's like exactly. Yeah, that is actually real cool.
Alright, so there's the motor dispensing the tape. It's coming out from here. This is our dev board, which is running that motor driver. You can see those are the outputs going to the stepper motor. We have a power supply over here, and then everything is going out through here.
This is Group G, Design, Build, and Test Energy Harvester for Smart Grid Meter. We're using the inductive energy harvester method to harvest energy around low voltage power lines. The first step to do this is to isolate one of the conductors in the low voltage power line. We have to do this because the magnetic fields will mostly cancel out each other out if we just snap the harvesting current transformer around the entire wire wrap, because there's two wires and the current is heading in opposite direction inside the wire wrap. Our current transformer, our harvester current transformer, has a 1 to 1800 turn ratio. We also have a second current transformer which we're using to take all our measurements with. It has a 1 to 3000 turns ratio. This output of the harvesting current transformer is hooked up to a full bridge rectifier and energy management circuit. This is the full wave bridge rectifier circuit. The input of this circuit is 7 volts, which is from the current transformer's output. The full wave bridge rectifier consists out of 4 diodes, which are connected to a smoothing capacitor, which is also a low leakage capacitor. Its capacitance is 330 microfarads. This is then connected to a step-down voltage regulator. The input of this voltage regulator is 4.5 volts to 15 volts. This voltage regulator takes the 7 volts and steps it down to 3.3 volts, which is needed for the microcontroller to work. This entire circuit converts AC voltage to DC voltage. It's
soldered onto a proto board, and the electrical connections are made on the back by using solder bridges. The next step in the process is the microcontroller.
The microcontroller is used to transmit data over Bluetooth Low Energy to a phone. The device that we use for measuring the current draw of the appliance is a current transformer that is connected to a burden resistor and a voltage divider. We need a burden resistor because when the secondary wires of the current transformer are left open, there is theoretically an infinite resistance across its ends, which can cause there to be an infinite voltage difference between the ends, as a result of which there can be a spark across the wires and that can damage your circuitry. The voltage divider is used so that we can scale down the reading from the current transformer to an acceptable level that the microcontroller can measure, and this range is 0 to 3.3 volts. The next step is the results.
Now the heater is going to start up. It will take a few seconds to connect the microcontroller to the phone. It will take a few minutes to connect enough data for it to create a nice sine wave. This data is going to be the current readings taken from the microcontroller of the circuit. This can be compared to the measurements taken from a current probe, from the sensor, and an oscilloscope. This is the result taken from the microcontroller for the current after about 12 minutes.
Thank you for watching our demonstration.
This is the final presentation for Group H, Design, Build, and Test, a wearable blind spot detection system for pedestrians and bicyclists, presented by Austin Pettit, Patrick Legaretta, Evan Gazzo, and Adrian Perez for EE 4800 Senior Project. Group H would like to express our gratitude to Dr. Okayo for his guidance and inspiration throughout the execution of this project. Group H is also immensely grateful for Dr. Hosan Lee for serving as our faculty advisor, providing his expertise and support, along with Dr. Theodore Grosch for providing his expertise with the radar module and amplifier design. Group H would also like to thank the Department for Electrical and Computer Engineering for providing its facilities and resources, along with Texas Instruments for providing resources to students and supporting the program.
Several technologies were used in this project. The IPM165 radar module is used as a detection device. The MC33079 operational amplifier is used to amplify the signal being received from the sensor. The LM293 comparator is used to modify the sensor output by transforming it into a square wave. The BeagleBone Black Wireless operates as the brains of the system and outputs code to the other implemented devices. An Adafruit 5-volt buck converter is then used to boost the voltage being used to power the BeagleBone. And lastly, the Adafruit USB charger is implemented to charge the 3.7-volt lithium-ion batteries that power the BeagleBone.
This iteration of the blind spot detection device employs 4 major components for operation. The IPM165 analog radar module serves as the sensor for the device and utilizes the Doppler effect to produce an analog representation of the object's velocity. The signal processor consists of the MC33078 operational amplifier and the LM293 differential comparator. The signal processor amplifies the radar module by approximately plus 20 dBm and produces a square wave for use within the BeagleBone. The processing unit of BeagleBone Black Wireless detects rising edges from the signal processor and triggers the alert system accordingly. A velocity is calculated using the Doppler shift equation from the square wave frequency. The alert system utilizes 3 vibration motors to alert the user to detected objects and their blind spot. Through future development, a mobile application can be used to receive alerts as well. All of these components are powered by a 6600 mAh 3.7 volt lithium-ion battery pack. A buck boost converter is used to power the BeagleBone Black, the radar module, the operational amplifier, and the vibration motors. A charging circuit is utilized to safely manage battery charging.
In terms of testing, 2 sets of trials were conducted with the radar sensor. One where the team member was holding a white poster board, and one tested without. The data from each set of trials are presented over the next several slides with graphical representations of each set. For each trial, the mean and max frequencies are both continually monitored while a team member moves from 12 feet to 3 feet away from the sensor. The velocity of the team member is then calculated using the Doppler shift equation, in which the frequency obtained from the oscilloscope is used for the Doppler frequency. The velocity was also calculated using the duration of the trial, so that a comparison can be made between the experimental velocity and calculated velocity. During the trials, it was observed that the maximum frequencies produced experimental velocities similar to the calculated velocities, whereas the average frequencies produced experimental velocities with a significant % error compared to the calculated velocity. This error can be due to human error, testing method issues, and non-ideal experiment conditions. Overall, it can be concluded that the poster board trials produced experimental velocity results that varied greatly from their calculated counterparts, while the human trials produce experimental velocities that are a lot more similar to the calculated velocities.
The bill of materials is as follows: a BeagleBone vibration motor, lithium-ion battery, Nylon Li-Poly charger, 3D printed enclosure, buck boost converter, and the IPM165 analog radar sensor, which is a much more inexpensive component than the previous sensors used, and the total cost coming to a $169.89. Some trade-offs and difficulties from this project were the lower output signal amplification due to a 5-volt instead of preferred 15-volt onboard power. This resulted in reduced effective range of the detection for the sensor. The difficulties faced were from fine-tuning the gain of the amplifier for higher quality output, determining a reliable base reference voltage for the comparator to trigger at, and interpreting data from the amp comparator circuit with the BeagleBone in the code.
The final results show that the sensor functions well at close range, Doppler frequency can be calculated from the comparator output, and the system is operational on battery power. In conclusion, the limitation of 5 volts supplied from the board significantly reduces the amplitude of the op-amp output and therefore the effective range. This iteration of the project introduces the idea of using radar sensors for blind spot detection. Future projects could focus on improving the sensor performance, exploring different radar sensors with additional features, and design a mobile app to interact with the device over Bluetooth.
We are Group I, and here is a video documenting the testing of our autonomous disinfecting robot.
Here is a demo of the robot following a box pattern with forward motion and zero radius right turns filmed in the beginning phase of development.
The robot is shown demonstrating a zero radius left turn and backwards motion. The functions shown here are the basic building blocks of a final robotic algorithm.
This demo shows the functionality of the bumper switches with a collision handling algorithm.
The robot is shown programmed with a wall-following algorithm. The demo shown here uses a proportional control system with a relatively high proportional gain constant, hence the wavy motion characteristic of overshoot and longer settling time. With an adjusted proportional gain constant, the response time is longer, but the results are still sufficient for the needs of the robot and with little to no overshoot.
Shown here is one of many tests where the response of the robot to a right corner turning scenario failed. Right turns on the test course took the most time to develop.
Of the aerosol disinfectant actuation.
This is the documentation of the testing of the final robotic algorithm. You can observe that the cans are actuating in an alternating pattern at a time interval of a half second. It should be noted that the team purchased 2 new cans of the Eon sanitizing mist for this testing, but the content of the new aerosol cans was not enough to last through a single test. This did surprise us, as we assumed that the contents of 2 cans would surpass the amount required for a full room disinfecting. Nevertheless, the concept still applies, and the robot can be observed actuating the 2 cans throughout its runtime. This algorithm is completely right wall following in design. It is implemented using a proportional controller, that is a periodic interrupt that dynamically adjusts the left and right motor duty cycles based on measured error calculated using the right sensor. With incoming data from the center and right IR sensors, this controller interrupt will also trigger 2 logical flags that are used to instruct the robot to handle the 2 corner turning scenarios, right turns and left turns. In each scenario, the robot makes extremely small translations and rotations. Many of these instructions followed consecutively result in a smooth, wide radius turn. Eventually, the logical flag that has been triggered in one interrupt will not be triggered in the next interrupt as the flag triggering condition is no longer present. And the robot is also programmed to turn off the motors and aerosol can actuators 4 minutes and 10 seconds after the start of runtime.